r equals 0. We have the singularity down here, again, r equals 0. We have, as I said, r equals 2m over here. We have r equals 2m over there. We have surfaces of constant r, like so. And we have internal surfaces of constant r that would be like this and like that. So this would be r equals 3m. This would be r equals m, for example. So, well, like we said this morning, so the surprising feature of the crustal diagram is the fact that we have two copies of everything. Two copies of the horizon, two copies of the singularity, two copies of each surface r equal constant. And you know, we might wonder, you know, what's the relationship, you know, between this and the original diagram that we started with that had matter in it. And it's pretty clear that the crustal diagram is missing a big piece. We don't have the matter that supposedly was there to begin with to form the black hole. So, well, two things. So if we want to describe the space-time, you know, if we want to have a space-time diagram that describes a black hole that results from gravitational collapse, we have to include the matter, and we have to understand that the Schwarzschild solution only applies outside the matter, not inside. Or we could choose to say that our black hole was always there, always existed, was never formed by gravitational collapse. It was just given to us at the beginning of the universe, and it will keep on existing until the end of the universe. So that's the distinction between you know, a black hole that was created by gravitational collapse and what's called an eternal black hole that was there, and that's, you know, terminology that you'll sometimes see in the literature. Eternal black holes would be basically maximally extended Schwarzschild black holes, where, you know, you don't see a beginning, you don't see an end, you just see a black hole at all times. And in fact, a black hole like this would be more than a black hole, because if this is, you know, if the notion of a black hole is that you have a region in which, try as you might, you will never escape, well, the region down here is the exact opposite. This is a region that you might try as you might, you will never be able to stay there. You will have to escape through the past version of the event horizon. So this is basically just the you know, the temporal opposite to what a black hole is, and, you know, the term white hole typically is used to describe this. So we have a black hole up here, we have a white hole down here, and the white hole is the exact opposite in the sense that whereas, you know, you can never escape from a black hole, from a white hole you have to escape. You cannot keep in. If you move forward with the speed, you know, if you move forward in time, you will have to make your way out of the event horizon. Okay, but if we rule out, you know, eternal black holes, if we say that this is probably something more of the, you know, a figment of the theorist's imagination, if we want to put the matter in, then we just have to, well, come up with a word line that's going to represent the evolution of the stellar surface as it undergoes gravitational collapse. And it's pretty easy to figure out what it needs to be, so we don't need to be quantitative here. In a diagram like this, it's pretty clear that a surface, you know, so that a stellar surface initially would start static, so it would be a surface of constant r. If we're talking about, you know, a spherical surface, we could imagine that this, you know, that the star would have, you know, some radius, maybe 3m, maybe something else, and that for most of its life, the star would actually be nice and static, so the stellar surface would coincide with the surface r equal constant. But at some point, the star would undergo collapse, and its, you know, radius would start decreasing, and it would start decreasing up here, and it would eventually cross below the event horizon, and then it would continue to contract until it hits the singularity at r equals 0. So that would be the word line that describes the behavior of the stellar surface up to the formation of a singularity, the formation of the horizon, all the way down to the formation of that singularity. And what we would have to understand, of course, is that anything that has to do with the Schwarzschild portion of the space-time only refers to the, you know, to the portion on the right, you know, the vacuum portion on the right of this word line, and everything else that's on the left, well, has nothing to do with Schwarzschild. it would be whatever is the interior solution to the star, you know, the metric that corresponds to having matter inside the star, you know, inside the collapsing star. So, and when we're done with this, well, there's not much that's left over. I think I made it a little bit too big, so I'll just extend the diagram a little bit. So this is r equals 3m. This is the event horizon at r equals 2m. This is the singularity at r equals 0, and only this portion of the Kruskal diagram survives. And what's inside basically would just be some stuff that corresponds here to the, you know, to the stellar center. And, you know, this would be basically the starting point t equals 0. And we would have, you know, a constant, you know, a constant radial, a constant r surface up until this time over here where collapse starts. And then we starts going, then the start, you know, the star starts going in, and we get the r equals 2m surface, and so on. So this is r equals 3m, and r equals, you know, larger values beyond that. So at this point, we start to recognize the picture that we had before. So all, you know, so the light rays that we used to draw over here, you know, starting from the center, we can draw them again. So if we start the, you know, if we start the light ray early when gravity is weak, well, in this diagram, in the Kruskal diagram, the light rays will always be propagating at 45 degrees anyway. So this is going to be one light ray that goes out all the way to infinity. This is going to be another light ray. So all those light rays propagate at 45 degrees because that's what the coordinate system is designed to do. So all of those light rays go out to infinity, but this is the light ray where, so this is the light ray that's emitted just before the event horizon where it goes to infinity, but it takes a very long time to get there. That information is not contained in the diagram because we sort of lose track of how long it takes for a light ray to go from the center all the way out to a given distance. But it's sort of suggested because here we see that we're sort of hugging this surface over here. Eventually, you know, they're going to cross, but it's going to take a very long time for this light ray to make it from the surface all the way out to r equals 3m. That's suggested by the hyperbolic, you know, shape of the r equal constant surfaces. At horizon formation, we emit a light ray from the center. It goes out for a while until it crosses the stellar surface, but as soon as it crosses the stellar surface, well, it's been caught by the gravitational field of the black hole, and now it will stay at r equals 2m forever. And that's exactly the behavior we had over here, except that here it was displayed differently. And finally, we have those light rays that start from the center, cross the surface, and then are recaptured by the gravitational field of the black hole so that they collapse into the singularity. Those light rays in the Kruskal diagram are represented by, you know, still at 45 degrees, but now they will be meeting with the singularity up here because the singularity is a space-like surface, and the light ray will always catch up with it. So here, the advantage of this diagram is that we see the causal relationship between things much better, and we have a diagram where the light rays are always at 45 degrees, so we know exactly on the diagram how to represent things that move with a speed slower than the speed of light. And with this diagram, we recognize very clearly that the r equals 0 singularity of a Schwarzschild surface, space-time, is actually a space-like surface. It's not a place anywhere, it's a moment in time. So sometimes people talk about the singularity at the center of a black hole, where it's really misleading because r equals 0 would represent the center if we were talking about the interior of a star. But after the black hole is formed, r equals 0 has become another one of those space-like surfaces that are represented by r equal constant. And what happens is that, well, when you go inside the black hole, you don't proceed toward the center, you just proceed in time. Proceeding in time means proceeding towards smaller values of r, and meeting the singularity at r equals 0 means that, well, you do that at some instant of time. So it's really a space-like surface. This information was not conveyed very well here, because here we were drawing the singularity as if it's a place that it's a place and that it persists in time. But in fact, that was a misleading way of drawing, well, it's the way we were drawing things. The price we had to pay in order to reconcile this with what's really going on is by tilting the light cones. So here, to really indicate that this was not a time-like surface, we had to tilt the light cones inward like this, which meant that, well, you know, this is not, you know, so with the tilted light cones like this, we recognize that this, you know, thing that seems to be moving in a time direction is actually not a time-like surface, it's a space-like surface because all the light cones are pointing toward it. So that's a piece of information that we see much better by just looking at the cross-cult diagram where all the light rays are straight at 45 degrees, and we see clearly what is a time-like surface like this, and what is a space-like surface like this, and what is a null ray, and so on and so forth. All right. So in a black hole spacetime that's produced by gravitational collapse, most of the crustal diagram goes away because we don't need anything that, you know, so, you know, portions of the diagram that used to refer to, so portion of the diagram that's below the stellar surface are completely irrelevant. But still, there's a lot of fun to be had by looking at the maximally extended Schwarzschild, you know, the crustal diagram in its entirety. So I'll come back to that, but, you know, it's useful to keep in mind that when we look at the maximally extended Schwarzschild diagram, crustal diagram, we introduce a lot of sort of fictional things that are not typically realized in physics, because if you want to build a black hole in physics, well, you pretty well need to have a collapsing matter, and anything that's inside the matter is not going to be described by the Schwarzschild metric, it's going to be described by, you know, the internal solution. But anyway, with this you know, warning, I'll go back to the crustal diagram and just do a little bit more with it. So any questions about any of this? All right. So a couple of things. So here's the diagram again. So this is V, this is U, this is the first singularity in the future, this is the second singularity in the past, and we have our surfaces of constant R this way, that way, this way, and that way. Okay. So you remember that to get to this diagram, we did this coordinate redefinition. So we started out with our simple, I don't know if I lost this, yeah, I did lose this. We started out with the simple null coordinates, the little u and the little v that were related to the original Schwarzschild coordinates, and I didn't call it r star before, but I'll call it r star now. So this is the integral of the r over f, which stands for r plus 2m log r over 2m minus 1. So we started out with those simple null coordinates that were closely tied to the original Schwarzschild coordinates. Then we did these redefinitions of the coordinates, and then we found that the resulting spacetime diagram had this richness to it that we didn't suspect ahead of time. That game can be played again, so we can do more of those coordinate redefinitions and introduce a compactification of the whole space-time onto a finite coordinate domain. And that's something that's pretty useful when you want to stare at the whole space-time and not have to say things like, well, r equals infinity is all the way over there, future infinity is all the way up here. If you want to do it in a way that's more precise and more convenient, there's a way of basically producing a map of the space-time that fits on a finite piece of paper. And that's an idea that was introduced, in the 60s by Penrose, that was generalized to black hole spacetimes by Carter, and it's a very useful thing to do for some purposes. So the idea is that instead of u and v, what we can do is to compactify compactify the coordinates. And the idea is that, well, we know that U will have an infinite range. It will range from minus infinity to plus infinity. V similarly will range from minus infinity to plus infinity. And what we have to do is to come up with some function, some mathematical function that will, compactify this range to a finite range. So any singular function that you can think of that achieves this can be used to do this, right? Can be used to do this compactification. And the one that typically is used is to say that we're going to introduce a new U. I'll call it U tilde this time. And I'm going to define it as the arctan of the original U. So that, while U ranges from minus infinity to plus infinity, the arctan of that will range from minus pi over 2 to plus pi over 2. Because you know that the tan function has singularities at pi over 2, so it goes to minus infinity at minus pi over 2. It goes to plus infinity at pi over 2. So we do it for U, we do it for V. And we introduce a range of coordinates that is now perfectly finite. And the idea for doing this is simply that, okay, well, instead of talking about a diagram that would extend, toward infinity in all directions, this way, that way, what we can do now is to compactify the whole causal structure of the whole space-time in one glance. So when you re-express everything in terms of those new coordinates, those rescale coordinates, so if you plot everything now in terms of U tilde, V tilde, what we find is that now the singularity will be described by a straight line like this. The other singularity will be described by a straight line like this. And then what used to be, V goes to infinity, the limit, sort of the asymptotic limit of space-time when V goes to infinity, translate into V equals pi over 2. So it's going to correspond to this straight line over here. And you're going to have another boundary like this. So this is, the original V going to infinity. This is the original U going to minus infinity. All of this has been mapped into a finite coordinate distance. And then you have a construction like this over to the other side. So the point is that this corner over here is all of Schwarzschild space-time, where anything that refers to infinity has been mapped to those finite boundaries over here. So just to redraw this in a way that contains a bit more information, I'll leave this here. I'll just redraw it. So usually it's done, so we still emphasize that we have a singularity, so we draw it like this. Then we have the horizons like that. Everything is still at 45 degrees because, by just relabeling, rescaling the null coordinates, we're not changing the feature that everything, the light rays will correspond to U tilde or V tilde equals to a constant. So again, the causal structure is still very simple. And you can draw a nice diagram like this, and that's all of Schwarzschild space-time, and it fits into a small part of the blackboard. So that's really the interest of doing that. Of course, by doing that, we pay a price. Obviously, we introduce huge distortions in the spatial relationships between things. So the distance between this point and that point is now infinite, but it doesn't look it here. So the distance between this point and that point is still infinite, but it doesn't look it. The distance between here and here is finite, but any distance between this point here or any point and one of the boundary points here becomes infinite. So we have to live with the fact that huge distortions have been introduced in the way to represent distances on the diagram like this. But that's fine, we live with this, and the advantage is that, well, now what's brought to light here, what's brought into a very nice, obvious way, is all the causal relationships between anything that's going on within the spacetime. So we have R equals 0 up here, we have R equals 0 down here, we have the first copy of R equals 2m here, we have r equals 2m over there. And for example, we see very clearly that if you're stuck, if you make your way inside the black hole somehow, that you may try to escape by going as fast as the speed of light in one direction or as fast as the speed of light in the other direction. But any way you do it, you will end up in the singularity. And if you move with a speed less than the speed of light, you will still go into the singularity. So here we see, we see the event horizon as a one-way surface very clearly. If you're outside, of course, you can still make your way out to infinity. You can still make your way inside the black hole. And all of that is revealed very clearly. If you're inside the wormhole, well, you will have to end up somewhere outside, either in this copy of the external region or in this copy of the external region. In any way, if you're inside the white hole region, you will end up outside r equals 2m, either in this direction or in that direction. Either in this copy of the external universe or in that copy of the external universe. So by just drawing, diagrams like this, you can see right away where things fit, what things are, and what the causal boundaries are. And you can see right away here that we have two very important causal boundaries, the event horizon, the future horizon, and then the past horizon. All of that is brought out very clearly. So those diagrams are very useful, and you see them all over the place. So it's a very common tool to analyze the structure of a space-time. Now there's a terminology that gets introduced when you draw a diagram like this, because one way that this helps you to do is to identify all the types of infinity that we can encounter in space-time. And basically that's all the different ways that you can go to infinity when you move in space-time, possibly moving in a spatial direction or possibly moving in a time direction. So there are notions of spatial infinity, there are notions of temporal infinity, and there are notions of null infinity. And it just depends on how you get there. If you go along a spatial direction, you will go to spatial infinity. If you go along a time-like direction, you will go to temporal infinity. And if you go with the speed of light, you will go to one of the null infinities that we have. So, for example, if I look at the Schwarzschild diagram and I say I'm going to move outwards on a space like geodesic, well, you will end up all the way over there to spatial infinity. So it's like a map where you see a portion of your territory, and then you know that the next town is over there, and you see an arrow pointing to that next town. Well, this is an arrow pointing to spatial infinity. Here the advantage is that I don't need an arrow to point to spatial infinity, because if I draw a space like geodesic that goes from this point over here all the way out to r equals infinity, I end up over here. And in fact, that point here, which is one of those metrical singularity, so this is a point. So this is a point in the map that's highly singular, because obviously all distances around this point are stretched to infinity. So this is a place over here where where all distances are distorted infinitely. But this is the point that you end up if you follow a space like geodesic in any direction that moves outward away from the black hole. So this is the endpoint of all space-like singularities, and that corresponds to spatial infinity. And that's usually denoted I0 in space-time diagrams like that. So that's the notion of spatial infinity, and we have one over here. We have another one in the other copy over here, so that's also I0. Well, another thing you can do is to start somewhere in space-time, say in this portion of the space-like diagram, and move in the time direction. You just stick around and you wait. And if you wait forever, you'll end up at time-like infinity. And on the Schwarzschild diagram, time-like infinity would be, okay, let's follow an r equal constant curve, and let's wait forever. You would end up far away into the upright corner over there. So again, you would need an arrow to point to the infinite temporal infinity. Here, you don't need to do that. If you follow an r equal constant word line in the Penrose diagram, you end up over here. And that point over here, where again you suffer an infinite distortion of all distances, this is time-like infinity. Well, I should say it's future infinity. And it's denoted I plus on space-time diagrams. If you go backwards in time, you end up over here. So this is this is past infinity. And that's denoted I minus. Yep?
Why isn't the entire singularity future infinity?
Say that again, sorry?
Why isn't the singularity also the future infinity?
Okay, so that point here is highly misleading because of this infinite distortion business. If you look at this point, if you approach this point from the outside, you're going to temporal infinity. If you approach this point from the inside, you're going to the singularity. So it's really completely disjoint in space-time, but because of this, distortion that I've introduced by doing the compactification of the coordinates, all of this looks as if it corresponds to one given point, but it's not one point. It's really, it's really very different portions of the space-time. So in fact, there's no connection between future infinity and the singularity. Right. So am I answering your question, or am I answering a different question?
Yeah. Also, is that where a time-like geodesics would go?
Yep.
It seems the entire upper right line is possibly where they end.
Oh, sure. So, no, that's right. So there's a distinction here. So all external time-like geodesics will end up here. But if you cross the event horizon, all geodesics will terminate on the singularity.
But couldn't they, or it's the distortion you're talking about, I guess. If their time-like curves are approaching that infinite point, they're never going to touch it because it's infinitely far away. Is that right?
Yeah, okay. That's right. So while they're at a finite distance, they're at a finite spatial distance, but they're infinitely separated in time, right?
So those are all time-like curves that don't cross
the event horizon. Yeah. If you have a time-like curve that crosses the event horizon, then the endpoint is on the singularity. Right. So future infinity is the endpoint of all time-like curves that do not penetrate a black hole, that stay safely outside. Okay, so we have a future infinity, we have a past infinity, we have a spatial infinity, and the other type of infinity we have are those that are relevant for light rays. So if you're a light ray moving outward of this singularity, proceeding all the way to infinity, you'll end up on this surface over here, which in this diagram looks like a nice null surface, and in fact it is. It's the limiting behavior of any null surface of constant constant v, sorry. So this is null infinity, null future infinity. And that's denoted with the script I, and it's pronounced scry, so that's an old standard in the literature, so that's something that distinguishes someone who's in from someone who's out. If you say scry, you're in. If you don't say scry, you're an outsider and no one listens to you. So you have to say scry if you want to be considered to be part of the club. So we have so null future infinity is where light rays end up, outgoing light rays end up, and those will emerge from the singularity over here. If you're sending light rays in, they will start over here, and they will end up into the future singularity. So that surface over here is null past infinity, and that's denoted scry minus. And there's another scry minus over here. There's another scry plus over there. So one advantage of a diagram like this is that you recognize at a glance what all the all the separate notions of infinity are. You can distinguish between future space-like infinity, time-like infinity, null infinity, and all of this is clearly identifiable on a diagram like this, and that's another advantage of having a compactified map like this. On a crosstalk diagram, you would have to distinguish this direction from other directions, and it would become a little bit confusing to distinguish all of these things. The big price to pay is, well, this heavily, this infinite distortion that we've introduced. And for example, the suggestion that at this point over here, time like infinity meets the horizon, meets the singularity, when in fact they never meet. So this is just an artifact of the map. The map becomes infinitely distorted here. So this is basically just an optical illusion. On a crosstalk diagram, of course, we would know that this surface is always separated from this surface, is always separated from that surface. So there would be no confusion. But in a diagram like this, while there's that risk of confusion when you look at those points a little bit too closely or take them too seriously, you just have to remember that this is not really a point. It's really just big portions of space-time that have been collapsing to that point because of this compactification. Yep.
It looks like, from the diagram, that it start in the white hole area. You can pass right through the bifurcation point and go right into the black hole. But would that take infinite proper time, or is that possible, or?
It's possible, and it doesn't take infinite proper time. So you can just let yourself follow this geodesic up here, and you will pass through the bifurcation sphere, and you will never have a chance to look at the outside world. You will be going from the white hole region into the black hole region. And I think it's true. It doesn't take. I think it's true. It doesn't take infinite proper time. In fact, it's faster than you would like. Probably.
So,
Yep.
if we think about both white hole and black hole occupying coordinates in space-time, and you come back to r theta phi coordinates, they have to play the same place, right?
No, because it's multi-valued. So r equal constant is not one place. It's become two separate places, right? Because of this. In these coordinates.
But if we convert it back to r theta phi, they're happening at the same place, right?
No. So the point is that the cross-goal coordinates, or anything like that, these are the coordinates that give you the maximal extension of the Schwarzschild spacetime. If you look at it in the original Schwarzschild spacetime, you would find that geodesics seem to terminate, or they seem to accumulate to r equals 2m, for example, but they accumulate in finite affine parameter or something like this. So you would recognize in that coordinate system that you're missing something, that the spacetime is not complete, and you would take those geodesics and you would say, well, let's just keep going along those directions, and you would gradually conclude that the initial coordinate patch that you had was only a partial description of the spacetime, and then you would recognize that all of those extra features have to be put in. So r equal constant, regardless of the coordinate system, r equal constant will always mean either, this surface over here, or that surface over there, or this surface over here, or that surface over there. There will always be two regions, two surfaces in the Schwarzschild spacetime that correspond to a given r. In the original coordinate system, we hadn't, we couldn't recognize this because we sort of designed our coordinates in a way that, that was suggestive of the fact that they were just a modest extension of spherical polar coordinates. And we always felt that r equals 0 should describe a center, and there's no such thing, beyond r equals 0, right? So there's no negative r is not defined. But that's one of the warnings that occur in GR, where you try to assign too much meaning to coordinates. The meaning of the coordinates always has to be revealed by the metric, and the metric is basically the thing that tells you how to, continue geodesics and make sure that you really have identified the maximal extension of your spacetime. Right. So the only way you can kill those additional features is to remember again that, presumably you need a collapsing star in it, And if you want to fit the collapsing star into the Penrose diagram, you just say, well, it had to start at in the infinite past. It had to follow an R equal constant word line for a while, and then it had to collapse, and it would follow a word line like this, and then everything on the left of this would not belong to Schwarzschild. It would belong to the solution that describes the stellar interior. So you can still get rid of all of this, and you can still replace it by the solution inside the star, like that. All right? Okay, let me mention one other aspect of the crustal diagram that's sort of amusing. So we've introduced the idea of the Penrose diagram that we'll come back to in a few minutes when I talk about Reissner and Nordstrom. We have this collection of infinities that sometimes is useful to talk about. But let me go back to the original diagram, the original Kruskal diagram. So that's V, that's U, that's the singularity, and that's the other singularity. In Schwarzschild spacetime, I haven't talked about this, so far we've been sort of focused on the causal structure of the spacetime. But in the Schwarzschild spacetime, we have a time-like killing vector. And if we were using the original Schwarzschild coordinates, that would be a vector that has only a component along the time direction. And we know that, well, this is a killing vector, that we have a time translational invariance in the spacetime. And I say time-like, but I'm going to have to be careful about this, because it turns out that this is not time-like everywhere. I know that this coordinate system is singular across the event horizon, so when I stare at the components of the vector field in Schwarzschild coordinates, I know that I have to be careful with that because I wouldn't be able to conclude from this that, for example, this vector field is nice and regular across the event horizon. So one thing you can do is to, again, take advantage of the Kruskal coordinates. You can do it in the Eddington-Finkelstein set, and that would be the same. But with the Kruskal coordinates, we can cover the full manifold, and we can work out the coordinate transformation between Schwarzschild and Kruskal, and we can work out the components of the killing vector in those Kruskal coordinates. So in u, v, theta, phi coordinates, what we find is that the killing vector will have two non-trivial components. One is going to be along the u component, the direction, and it's going to be given by minus u over 4m. And along the v direction, it's going to be v over 4m. And it's going to be 0, obviously, in the angular directions. So we can look at the behavior of that killing vector and see what it looks like. Well, outside the black hole, it's pretty clear that the time-like killing vector will point in the time-like direction, which means it's going to be tangent to orbits of surfaces r equal constant. So if we plot a word line r equal constant, the time-like killing vector will be tangent to this, because that's the time direction keeping r fixed. That's where the killing vector is going. And outside the black hole, we get the usual notion that the time-like killing vector is future pointing and defining a translation in time. If we go on the event horizon, u is equal to 0, and this component of the killing vector is 0, and that means essentially, given the form of the metric, that t is null on the event horizon. So if you plot this vector on the event horizon, it only has a component along v, it has no component along u, so the vector points in that direction on the event horizon. So it tilts from being time-like to being null on the event horizon. If you go inside the black hole, well, you can, I think, quickly convince yourself that the time-like killing vector will be, again, tangent to an R equal constant surface, but that R equal constant surface now is space-like, not time-like. So the killing vector goes from being time-like to being null to being space-like, and it tilts this way as you move inside the black hole. If you're over here, then things become interesting. If you're over here, v is equal to 0, and t points in the minus u direction. So the tilt continues, and if you're over here, the killing vector points down in the negative u direction. If you go out on the other side of the space-time, this is still an R equal constant surface, but now the time-like killing vector points backwards in time. If you're back here on this copy of the event horizon, well, you find that the tangent vector is still that the killing vector is still null, so it still goes null here. So here it's time-like. It's just that it's backward pointing, past directed, not future directed. Here it's still a null vector, and but it's again past directed because in this case when u is equal to 0. No, I'm getting this wrong. It's pointing along the plus v direction.
But v is negative.
Yeah, v is negative. Oh, you're right, v is negative, so it has to go down. That's right. Thank you for that. So it points down like this. And over here, it's going to be, again, tangent to an R equal constant surface, but now it's going to be pointing in that direction. So, and if we're down here, then the killing vector goes back toward being future pointing, and then it the tilt, it goes back to being future directed on this side of the diagram. So the killing vector has a pretty interesting flow in the Kruskal diagram, and the fact that it's past directed on this side is connected with the fact that surfaces with constant t in this diagram, which I haven't talked about so far, surfaces with constant t end up being straight surfaces that cross the bifurcation to sphere over here. So this would be a t equals 0 surface. This would be a t equals 1 surface. This would be a t equals 2 surface, and so on and so forth. So as you move up here in time, you cross surfaces in increasing order. But here, because they continue across that bifurcation, the future direction here gets flipped into the past direction over there, and the time-like killing vector just follows that evolution. So orbits of the killing vector go backwards in time over here, and they go forward in time over here. An interesting place in the space-time is right here. And you see that there, u and v are both equal to 0. And what we get here is that the killing vector actually vanishes on that surface. So that point over here, it's called the bifurcation to sphere. The bifurcation surface. That's actually a fixed point of the killing flow. The killing flow basically comes to a halt there. It has nowhere to go because the vectors are just pointing in opposite directions from all directions. So the vector field for smoothness has to be 0 right there. So it's an interesting property of the bifurcation to sphere that it corresponds to a place where the killing vector disappears. It vanishes at that point. So that is a definition of the bifurcation to sphere. And it's that interesting place in the Schwarzschild spacetime where we have an intersection between the two horizons, and it's also the place where the killing vector goes to 0. Okay. Well, that's pretty much all I wanted to say about the Schwarzschild spacetime, and notice that we've done very little work in terms of solving geodesic equations or doing anything like this. So there's the whole discussion of how particles move and orbits and things like that. I mean, I'm skipping this because I'm, expecting that you've seen that in an earlier course. So all the stuff about geodesic motion and Schwarzschild, I'm going to skip. So there's one thing that I'm going to do just now before I move on. But other than that, it's pretty much what I wanted to say about the Schwarzschild solution. Basically introduce this idea of a Penrose diagram and review all the features of the Kruskal diagram. Those are basically the essential points I wanted to make. All of this brings out this very essential idea that in this space-time we have a clear distinction between the region inside the black hole in here, which is completely inaccessible causally from the outside, and everything else where we can have causal relations between what's going on outside and what's going on outside. There's no causal relation between what's going on inside and what's going on outside, because all of this is to the future of anything that's down here. So you had a question?
What's the direction of future on the left side of that diagram?
The direction of future? Well, for me, future is always up, right? So if I move forward in time, in any sort of meaningful sense, I have to move up in the space-time diagram. Now, is there a contradiction between this and the fact that the time-like killing vector is actually pointing toward the past? Well, no. I can flip the sign and introduce a new convention for the killing vector so that this time direction will agree with this time direction.
But your killing vector field is not smooth.
Which one?
The T.
Well, if I flip the sign here, I'll have to flip the sign over here too. So
that side becomes past director.
If there was any possibility of communicating between the two sides, we might be in trouble. But there's no way you can actually communicate between the two sides. If you send a signal over here, well, it will go into the black hole, but you'll never notice it outside here, and so on and so forth. And in fact, any attempt to travel to the other side would require moving faster than the speed of light, so you can't do that. So the local time convention here can differ from the local convention there without introducing any pathologies or anything like that. But you're right. If you flip the sign here and you don't flip it here, then you introduce a singularity in the time-like vector that would have to be resolved, for example, the same way that you resolve a singularity and the log function in a complex plane. You just introduce a cut, and you make sure that you don't go across the cut when you evaluate your function. That would be a similar kind of fix. All right, other questions? Okay, just let me do a little calculation to start talking about the behavior of, the description of the horizon in terms of its null generators. So that's going to be basically a prelude to what we're going to be doing, a lot more next time. So let's look at what do I want to say here? Okay, so I want to look at the killing vector on the horizon. I want to analyze its behavior on the horizon where it becomes null. And what I want to extract from this is the notion that, well, we know that the event horizon is a null surface. We know that T becomes null. I mean, we're going to find out that we know that T becomes null on the hypersurface. So the vector T alpha will have this, this joint notion of being both normal and tangent to the event horizon, and it's going to be tangent to the null generators of the event horizon. And I want to start describing this a little bit, because that's really going to be the starting point to a discussion of the event horizon in very general terms when we get going with all this. So I have to work in a coordinate system that's going to be regular across the event horizon. I don't want to use Kruskal because Kruskal is too clumsy and requires a little bit too, it requires too much work. For one thing, I would have to think of inverting this relation, or at least keeping R implicit. I don't want to do that. So what I'll do instead is to go back to Eddington-Finkelstein and work in that coordinate system as I describe what's going on across the event horizon. And something I should have mentioned before is that, so the cross-col coordinates are good everywhere, where they allow me to access all portions of the Schwarzschild manifold all at once. If I'm using cross-col coordinates, the ones that I talked about this morning, what I find is that it's only this portion over here of the space-time that's covered by the coordinates. The coordinates are perfectly regular over here, but they do not allow an extension beyond the past horizon. So the past horizon is basically inaccessible in those Eddington-Finkelstein coordinates. There's ways of working with this. You can introduce different coordinate patches using Eddington-Finkelstein. You can use V and R, but you can also use U and R. And by patching those patches together, you can cover the whole thing. But if I'm working around the future horizon and I have no particular need to describe what's going on in the past horizon or in the past white hole region or on that side of the cross-col diagram, I'm perfectly happy with the coordinate system that covers only this, because those are really the essential, region of the Schwarzschild space-time. And all of this, of course, would not be relevant if we have a collapsing matter. Okay, so let's look at the Schwarzschild metric in those coordinates. So I had it before. So I have, sorry, that's V. So we have that, and we still have that F is 1 minus 2m over r, so that it vanishes at r equals 2m. Now I can do the same thing I did this morning and consider the transformation of the coordinates. Okay, I've lost that. I can look at the components of the time-like killing vector in the new coordinates. I can do the coordinate transformation, and if you remember what we did this morning, there was a non-trivial combination of the time and radial component that gave me the v component, but here there's no radial component. So you can quickly calculate that in this coordinate system, T alpha is directed along v, and it has no radial, no angular component. So this is v, r, theta, and phi. So the killing vector points in the direction of v, and this you can basically infer from the fact that there's no explicit v dependence in the metric. So we get a killing direction in the direction of v for the same reason we had a killing direction in the direction of t in the original form of the metric. All right, so that's the time-like killing vector. In this coordinate system, we can calculate the norm of the killing vector. And in that coordinate system, but it's a scalar quantity, so that's going to be true in any coordinate system, we pick up only the v component of the metric, because there's only a v component to that vector, and that's equal to minus f. And we find, sure enough, that this is 0 on r equals 2m. So this is the result, again, that the vector is time-like outside because f is positive. It's null on the horizon because f is 0, and it would be space-like inside the horizon because f is negative inside the horizon. So t is so t is null on the event horizon. So t null on the horizon. And a little bit more thought, going into this. So basically, you can recognize the fact that t being null on the horizon and pointing in the direction it points means that it's actually, at once normal and tangent to the horizon. So it's normal to the horizon, and it's also tangent to the null generators of the horizon. And this goes back to properties we studied before when we were looking at hypersurfaces and looking at congruences. So our event horizon is going to be a null surface that's again generated by null geodesics, and those null geodesics are going to be the killing vector T alpha is going to be tangent to those null geodesics. One thing I should verify is that T alpha will satisfy the geodesic equation on the horizon. The orbits of the time-like killing, the orbits of the time-like killing vector are not geodesics outside the space-time, outside the horizon, because the orbits, as we talked about before, the orbits of the time-like killing vector are surfaces, are word lines r equal constant outside the horizon, and those are not geodesics; they are accelerated word lines. So the killing vector certainly will not satisfy the geodesic equation anywhere outside. And it's not going to satisfy the geodesic equation anywhere inside as well. But it turns out that on the event horizon itself, it will satisfy the geodesic equation. So let's calculate this. So here I'll skip some of the details, but I'll just calculate the covariant acceleration associated with the killing vector, and I'll just write it out in components. Anywhere in the space-time, it would be given by half the derivative of f times half f times the derivative of f. And unless f is equal to 0, we find that the outcome is not geodesic. When f is equal to 0, this goes to f prime at 2m, 0, 0, 0. And we see that the acceleration ends up being proportional to the vector itself. And that means that we have the geodesic equation, but the geodesic equation in its generalized form where the parameterization is non-affine. So in fact, on the horizon, we get some quantity kappa times T alpha beta, where kappa is recognized as half the derivative of m evaluated at r equals 2m. And the derivative of f, well, we can calculate it easily. So the derivative of f is going to be 2m over r squared. R is equal to 2m, so we get 2m over 2m squared, but there's an extra factor of half. We get 1 over 4m. And that's a quantity, well, because 1 over 4m is basically m divided by, excuse me, 2m squared. That's the mass of the black hole divided by the radius squared. That's called the surface gravity of the black hole. So this is a quantity known as the surface gravity. And the conclusion is that on the horizon, we have that the killing vector satisfies the generalized form of the geodesic equation. And that's true only on the horizon, because it's only on the horizon that I can get rid of this additional term. Now, what we learned from all of this is that, well, here we have the generators parameterized by v, because that's what this equation here means. It means that a displacement along a generator is going to be given by this. So T alpha is dx alpha dv. That's what we see here. So the generators are parameterized by v, my null coordinate that we introduced before. But what we see from this is that this is not an affine parameter. So my generators, if I'm going to use v as a parameterization, as I've done here, and if I'm going to use the time-like killing vector, or the killing vector as its tangent vector, I've agreed that the parameterization is not going to be affine. if you would like to find an affine parameter, you don't have to look very far. The cross-goal V is an affine parameter. You remember way back when you solved the problem on how to introduce an affine parameter if you didn't have an affine parameter in the first place in the case of null geodesics. There's an exponential relationship, and if kappa is constant, which is the case here, well, that's the relationship that comes out. So this is the non-affine parameter, this is the affine parameter, and they differ from each other by an exponential relation. Right? So this is just a prelude to what we're going to be doing next time, where we'll exploit these kinds of relationships and do that for very general black holes. So any questions about this little calculation here? So here we did the calculation so it was important in this calculation that we did things in a sensible coordinate system because we were taking the limit where we would go to the horizon. And for example, I was doing this in terms of vector components, and it's important to do that in a regular coordinate system because otherwise, if I were doing this in Schwarzschild coordinates, we would get all sorts of things going to 0 or to infinity, and that would all be an artifact of the poor coordinates. Whereas here, I do the calculation cleanly. I could do the calculation cleanly because I have a regular coordinate system, and there's no ambiguity. There's no, pathologies that come into this calculation. So that's another, illustration of the advantage of the Eddington-Finkelstein coordinates. All those calculations can be done very, very efficiently, very simply in that coordinate system. Okay, so that's what I wanted to say about Schwarzschild. And I guess for the remainder of the time today, I want to talk about the charged version of the Schwarzschild spacetime where you allow the black hole to have a charge. All right, so it turns out that when we talk about black holes, so I've already mentioned the Israel uniqueness theorem that says that when you have vacuum and you have a non-rotating black hole, you will always end up with a Schwarzschild black hole. There's a simple extension of that theorem that says that if you allow for the existence of an electric field or an electromagnetic field, more generally speaking, there's an extension of the result that says that it's possible for the black hole to have a charge, and the solution for this is called the Reissner-Nordström solution for the people who came up with it initially. So the Reissner-Nordström solution is an exact solution to the Einstein-Maxwell equations, where you can have a charge inside the black hole, everything is spherically symmetric. So the electric field outside looks like the usual 1/r² electric field, but the metric changes because now you have this distribution of electrostatic energy, everywhere outside the charge, and that modifies the mass function. It modifies the space-time. So it's possible for a black hole to have a charge, and the other quantity that it can have is angular momentum. But after that, you're done. So that's the famous no-hair theorem that says that in any circumstances involving gravitational collapse in 4 dimensions, the resulting black hole must be a Kerr black hole or a Kerr-Newman black hole. And what it must, the only characteristics that it has is to have mass, possibly charge, and angular momentum. Charge is, it's not terribly realistic from an astrophysics point of view. So you don't have bodies in astrophysics that accumulate large macroscopic, charged matter. So matter on the whole is neutral. So if a body acquires charge, typically it will acquire the exact and opposite charge, so it will neutralize very quickly. So people in astrophysics don't really talk about charged black holes very much. There's no need for them. There's no evidence that they exist. But as a theoretical result, as a theoretical discussion, it's certainly possible for a black hole to have a charge. We can imagine throwing a lot of charge into a black hole and keeping the charge in place, making sure that it doesn't neutralize by accumulating the opposite charge at some point. So we just keep the black hole charged. Anyway, so the Reissner-Nordstrom black hole has a mass m and a charge q, and the metric looks very similar to the Schwarzschild metric. I'm going to go back to the usual Schwarzschild coordinates here. But the metric function is different. There's an extra term that comes from the charge. And it's pretty easy to understand where this is coming from. So this is, this expression for the metric function I can rewrite in terms of a varying mass function. So I can always express the metric function in terms of some mass function that would vary with m, with r. And in this case, the mass function would just be the original mass of the black hole minus what comes from the charge. And again, it's easy to understand where this is coming from, because if I calculate, I can calculate the derivative of the mass function, and that will be equal to q squared over 2r squared. And I can recognize that 4 pi times r squared times m prime, well, that's actually something that you would see in the field equations. That's something that you would read off from the field equations as describing the mass density in your space-time. So that's exactly the same equation you would get in Newtonian gravity, but now it's formulated exactly in GR. So the 4 pi r squared, the derivative of the mass function, corresponds to the mass density. So that that's just saying that you get the mass by integrating the mass density across spherical shells, from an initial radius to a final radius. And if you do this calculation, you find that, sorry, I've got it backwards. The density is the mass derivative divided by 4r squared, so that the mass derivative is really, the mass density times the area of the shell. And if you do this calculation, you find that this is q squared divided by 8 pi r to the 4th, which is 1 over 8 pi q over r squared, all squared. And that, I think you can recognize, this is the electric field produced by my charge. So this is E squared divided by 8 pi. And this is exactly the expression you would get from the Maxwell stress energy tensor. This is the energy density contained in the electric field. It goes like E squared, and there's the factor of 8 pi, 1 over 8 pi in front of it. All of this is done in CGS units, so there's no, epsilon naughts or anything like that appearing in this calculation. So what does this say? Well, it says that by modifying the mass function like this, I'm actually accounting for the distribution of electrostatic energy that comes from the electric field that comes from the charge. And the sign works out because, mathematically it works out because I get a positive mass density after differentiation, and I get something that does describe what we would expect for a radial electric field produced by a charge at the center. The minus sign also works out, physically speaking, because what the mass is, the mass function is, as a function of r, is the mass contained within radius r. If I go to infinity, I have the full mass which is m. M is the total mass of everything in the space-time. And if I go to infinity, r going to infinity means that my mass function in a shell of radius r equals infinity is the full mass of the space-time. If I bring my spherical surface down to a finite radius, I'm leaving out all this electrostatic energy outside the surface, right? So m inside r will be all the mass minus what I leave out when I bring my boundary from infinity down to a finite radius surface, and that's the minus sign over here. What I'm leaving out is all the stuff outside, and as I keep shrinking the surface, I keep leaving out more stuff, and I get a smaller value for the mass inside R. You have a question?
Is this what people usually sometimes call the Misner-Sharp mass?
Yeah, it's the Misner-Sharp mass. Okay.
So,
Yep.
so capital M is not the mass of the singularity.
No,
It's the
it's the total mass of the space-time, including all the electrostatic energy. Okay, so that's where, so in the book I give you more details about the derivation and also tell you what the solution to the Maxwell equation are. But basically the solution to Maxwell's equation is simply the statement that the electric field is Q over R squared, as you would expect. So there's nothing very mysterious here. And the claim is that this is an exact solution to Maxwell's to Einstein-Maxwell's equation, and it describes a black hole. One new feature is, there's a couple of additional features that come from this solution. The fact that if you are looking for horizons, you would look at places where f vanishes, and now it's a quadratic equation for R, and you find that there are two places where f vanishes. So it looks as if here we have two distinct horizons instead of just one at for the Schwarzschild spacetime. So here, when we look for horizons, we look at f equals 0, and we find that there are two solutions, r equals r plus and minus, which are given by m plus or minus m squared over q squared over, that's it? Is it over 2?
no.
No. Yeah, that's it. That's it. So we have two distinct horizons, and now we have to understand that. I mean, what's the meaning of this new horizon? What role does it play? And all that. One thing that we see here is that if we want real solutions instead of complex solutions, we're going to have to be sure that m is larger than q. And in fact, there is a limit as to how much charge you can accumulate inside a black hole before you destroy the black hole, or before there's no black hole to begin with. It's very important here to impose that m is always larger than the absolute value of the charge. If you don't have that condition, you don't have a black hole. What you would have instead is a naked singularity. There would be no places where f would change sign, and there would be no horizons in your space-time. All you would have is a singularity at the center. Yep.
To understand that mass density, if you integrated it on all space, you would get the integral of e squared over 8 pi times the size of space plus your big M, right?
Yeah. So the big M would appear as an integration constant, because the integral of this from an inner radius to an outer radius would just give you basically the mass contained within this. Anyway, it would give you a constant, and then you can adjust that constant so that you capture, so m would essentially enter as an integration constant in that calculation.
Is it interpreted as the mass contained at the point?
So when you do this integral, you wouldn't want to go from r equals 0 to r equal infinity, because that would be meaningless. So what you would choose to do is to say, I'm going to cut off the integration at some inner radius, for example, the horizon radius. You integrate outward, and then you would have the total mass expressed as, all the stuff plus whatever is inside here. And all of that basically would combine to give you that. So in a sense, this would be, if you were to break it this way, you would have m broken down into, the total mass into, well, there would be a contribution from the black hole region and then the rest of it. But I think it's better to look at it, backwards. So I think it's better to integrate this without boundaries. I mean, without limits, and just adjust the constant, and then we recognize this as being the total mass of the space-time, the one we would read off at infinity. You have another question?
Can't you start with the Schwarzschild and put charge in it until Q becomes bigger than M?
Yeah, and what would happen then, right? So you can start with a Schwarzschild black hole. You can keep imploding spherical shells of charge, right? As you do that, you would have to be careful because, as you keep imploding charge, you would increase the charge of the black hole, but you would also increase the mass. Well, maybe you can tune things in such a way that you would increase the charge more than you increase the mass. Well, at some point you would reach a situation where the charge is very large and you're trying to implode even more charge. Well, okay, so that shell of charge, that last one that you think will overcharge the black hole, will actually have to, it will have to compete because it will feel the gravitational attraction of the black hole, but it will feel the electrostatic repulsion of all the charge you put there. And in fact, if you do it with spherical shells, you would find that, well, in the end, you'll never be able to overcharge the black hole because electrostatic repulsion will win. So that the last charge, the last shell that you're trying to send in will in fact bounce back before it reaches the event horizon. So, and in fact, that's connected to the third law of black hole mechanics that we'll talk about later. If you try to invent a process that will turn a black hole into something that's not a black hole, you will not be able to. There will be some mechanism, some agent that will prevent you from breaking that inequality, for example, in this case. Yep.
When you're talking about the difficulty in supercharging a black hole, do you mean under geodesic motion it won't be able to enter, or is that like
under the so if you're trying to if the black hole already has a charge and you're throwing some charge into it, that charge will not follow a geodesic because it will feel the electrostatic force exerted by the big charge inside the black hole. So it's not going to be geodesic motion. It's going to be motion against the force exerted by the black hole through its electrostatic.
But what if there was a driving force? I guess
if
there's a driving force, something is.
Oh, something so you just push against the particle's best interest. You would say against the shell. So you just keep pushing on it. You can imagine doing this. But now you would have to account for the energy that you're putting into the shell by virtue of pushing it in, and you find that this would also contribute to increasing the mass, and those scenarios also fail. So there's been a whole literature of thought experiments of that sort that would try to point out, find a way to break the inequality and drive the black hole beyond the black hole state, and that's never worked. I should mention that there's one research problem that's still active, and my students and I are working on this. That's the problem that's the scenario where you would have an almost extremal black hole, a black hole that's almost exceeded its bound, and instead of throwing a shell, you're going to throw a one-point particle with enough charge to, in principle, overcharge the black hole. And there seems to be some, it's not quite settled yet whether it will always be true that last charge is going to be turned around before it crosses the event horizon. And in fact, if you work on this problem and you ignore, so if you take only into account the force exerted on this last charge by the charge of the black hole, you will find that there's a region in parameter space that allows you to overcharge the black hole and have the particle cross the event horizon. So as of the late 90s, there was this open problem that said basically said that if you only account for the force acting on the charge created by the black hole, there's a set of parameters you can choose among the mass of the charge itself, and the energy you give to the charge that will allow you to send the charge inside the black hole and overcharge the black hole to produce an unknown state that violates this bound. What this argument forgets, or what this argument doesn't take into account, is the self-force acting on the charge created by its own field, which turns out to be very important for this process, but that's something that no one could calculate until very recently, and that's something that I've been working on together with my students, and now we have the technology that we need in order to calculate the self-force acting on this charge while it falls toward the black hole. And we believe, although we haven't proved it yet, but we're in the process of doing this, we believe that the self-force is going to be the mechanism required to make the charge turn around before it reaches the event horizon. So basically the point is that, well, trying to break this has been considered in the past, and there's been lots of arguments that have been sort of turned around that have been, shown to be, impossible. So there's lots of scenarios that have been ruled out to overcharge a black hole, and the last one that I'm aware of is the one we're working on right now, and it requires quite a bit more physics than people expected at the beginning, and because of that, it's pretty interesting. And in particular, it's pretty interesting to me that the self-force acting on a particle, which is a real effect that's never been shown to be relevant to anything, could actually be very relevant to establish cosmic censorship once and for all. So that's something that certainly gets me excited. Okay, I didn't have time to finish this, and I'm really getting exhausted because of the overheating that's going on here. So I think I'll just stop it here, and next time I'll just finish the story about Reisner-Nordstrom. The main thing is about to understand the meaning of those two horizons and see what we can say about them and see how the causal structure of that space-time is very different from what we've seen here. And then I'll talk about Kerr, and Kerr introduces all sorts of other interesting elements, but after that we'll clear the way and we'll be able to do black holes in very general terms without having to rely on the details of solutions. It's something pretty fascinating about black hole physics, that you can do a lot of it without ever writing down a metric. You can infer all sorts of properties of black holes without looking at specific metrics and keep the discussion very, very general. Okay, so let's